Where does time begin? Where does it end? Does time have an end? Was there time before the Big Bang? Just as everything has a lifespan, so too does our solar system. When our solar system reaches the end of its life, will time still exist? Is time something that flows independently of everything else, a straight, unbroken line? According to figures like Newton and Galileo, the great masters of classical physics, time is absolute, unchanging, fixed, and flows independently of everything. Newton is the name most synonymous with time in the public mind. One day, a young man working at a patent office in the city of Bern wrote something in his notebook. Newton, I am very sorry. With these words, he was challenging Newton, Descartes, Galileo, and dozens of other scientists, the names that had shaped history. Albert Einstein was essentially telling some of the most celebrated scientists who ever lived that they had gotten it wrong. This was the same man who, as a student, had once said, "This fact or that fact doesn't interest me. I want to learn how God thinks. Everything else is just detail." And what else could you expect from a man who, even in the hour before his death, picked up his notebook and pen in an attempt to take the final step towards solving the mind of God, still working on his theory of everything? Truly understanding science is impossible without first understanding Albert Einstein. But today's subject is time, and Einstein has something to tell us. To understand time, we need to look back in time, to where it all began. We won't go as far back as the Big Bang or the philosophers of antiquity. We can discuss those separately if needed. But we do need to take a look at the 16th century, when the phenomenon of time was first studied from a scientific perspective. What a remarkable century it was. The 16th century produced an extraordinary number of brilliant scientists, didn't it? Galileo, Newton, Barrow, Descartes. It was a century that stretched into the 17th century, an era some have called the Age of Enlightenment. The first man to work scientifically on time was Galileo Galilei. The concept of time that would be accepted for centuries then took nearly its final form with Isaac Barrow and Isaac Newton. According to these scientists, as we mentioned, time is absolute, unchanging, and fixed. That is the very essence of what we mean by Newtonian time. And this definition of time, accepted as constant, was a phenomenon that moved at a fixed rate at every point in the universe, identical for everyone, measurable yet imperceptible, beyond sensation. Newton believed that time and space were two entirely separate entities. He had convinced himself that time would continue to exist even if everything in the universe ceased to be. As Shakespeare's famous line goes, all the world's a stage, and in Newton's view, the one unchanging backdrop on that stage was time. Time was the one constant he never altered in any of his laws, and therein lay a problem, one Newton was never able to solve in his lifetime. A problem he believed was the work of God, something beyond our perception. The most telling evidence of this was hidden in the movements and orbit of Mercury, the innermost planet in our solar system. Newton's laws could calculate everything, the motion of a falling apple, the movement of ships, even the precise orbit of the Earth. Yet Mercury stubbornly refused to conform to these calculations. There was always an irregularity in its orbit, something that simply would not fit the equations. It must be the work of God, Newton said at this point. Some scientists attributed Mercury's anomalous movements to another object, a planet we could not see, because that was the only way they could explain them. Yet it didn't feel right. They could not reconcile Mercury with any science-based formula. And as long as time was considered constant, they never would. Now I'm going to ask something of you. I know it's difficult, but I want you to forget everything you know about time. Forget how time progresses, how it flows in a straight line, how we live and die along that line. Forget all of it. Forget it because we need to completely dismantle that perception. Because it is wrong. Who says so? No, the person you're thinking of is coming in a moment. First, it was Wilhelm Leibniz who introduced this idea. For Leibniz, there were events that came before, after, or simultaneously with one another. Time simply helped us sort and categorize those events. Then Immanuel Kant joined the effort to re-examine time. Kant argued that time was not something that existed on its own, nor was it a sequence of relationships among independently existing things. In other words, it didn't merely file events away. According to Kant, time was simply the way our minds organized the experiences we had. He proposed that things existing independently of our minds, things beyond our perception, were not in fact situated in time at all. How could something we do not perceive exist within our time? Could this be considered the first attempt at a theory of multiple realities? And then, the man we had been waiting for. Albert Einstein would put the final period on all these debates. In 1905, he widely regarded as the most brilliant year in both physics and Einstein's own career, Albert Einstein published 4 groundbreaking papers, one of which was the special theory of relativity. A decade later, after an intense period of focused work, he published the general theory of relativity, cementing his name in golden letters in the history of science. What is time? This was the question that occupied Einstein's mind most deeply, even as someone who greatly admired Newton. Because after examining the equations in Maxwell's work, Einstein's thinking had fully crystallized. The one constant in the universe was the speed of light. The only thing entirely independent of us, indifferent to our direction or position, was the speed of light. And if that was true, then everything we had learned needed to change, especially Newton's laws, because time could not be constant. Let's work through an example. Imagine a scenario in which the sun suddenly ceases to exist. Under Newton's law of gravity, the Earth would instantaneously break free from its orbit and begin drifting into the void of space. And this would happen immediately. This is because, under Newton's law of gravitation, you can think of the gravitational force between two objects as a rope, a fixed instantaneous connection. But according to Einstein, no such event could occur, because the one constant in the universe is the speed of light, and nothing can exceed it. The speed of light is our absolute limit. It takes approximately 8 minutes for sunlight to reach us. And since gravitational force also travels at exactly the speed of light, if the sun were to vanish right now, we could continue for 8 full minutes without noticing a thing. This theory became one of the most significant in the history of science. Here is something that strikes me as remarkable. Albert Einstein might never have discovered this, and we could have gone on living under Newton's laws without ever realizing the difference. Because Newton's laws don't produce errors we can detect in daily life, they work correctly about 99% of the time. But that 1% that causes no trouble for the rest of us was a problem for minds like Einstein's, and in his view, everything deserved an explanation. How did Einstein arrive at this conclusion? In truth, Einstein had sensed it at the age of 16. In one of his famous thought experiments, there was a train and 2 people, one inside the train and one outside watching it passes. The train was moving at an extremely high speed. Now imagine that behind this train, at intervals of 100 meters, there are 2 trees, and at the exact same moment, lightning strikes both trees. According to Einstein, for the person standing outside the train, both strikes happen simultaneously. But from the perspective of the person riding the high-speed train, the lightning strikes the first tree first, and then, a moment later, the second. The same event, yet 2 different moments in time. How is that possible? Let's try to make sense of the constancy of the speed of light with another example. Picture 2 cars driving side by side, each at 60 kilometers per hour. For the passengers in each car, the other car appears to be stationary, not moving at all. But if one car accelerates to 80 kilometers per hour, then from the perspective of the car doing 60, the faster car appears to be moving at 20 kilometers per hour. That is our everyday intuition about speed. But this logic breaks down completely at the speed of light. The speed of light is precisely 299,792,458 meters per second. For the sake of simplicity, let's call it 300 million meters per second. Now imagine we build a rocket traveling at 200 million meters per second, and we travel alongside a photon, a particle of light. Under normal logic, if we measure the speed of that photon from our rocket, the result should be 100 million meters per second, right? But it doesn't work that way. No matter where or how you measure it, the speed of light will always be exactly 299,792,458 meters per second. E equals mc squared, the most famous equation in physics. Here, E represents energy, m represents mass, and c squared is the speed of light squared. When Einstein first wrote this equation, he expressed it as m equals E over c squared, meaning energy and mass are interchangeable. In other words, energy and mass are fundamentally the same thing. Everything you see and know is at its core energy. You, me, everything, all composed of energy. And we are talking about an enormous amount of energy. Consider a needle. If we could convert every atom that makes up that needle into pure energy, it would release the equivalent of 18 kilotons of TNT, a force approaching the power of an atomic bomb. This equation, and by extension Einstein himself, tells us the following. As the speed of an object increases, so do its energy and mass. As it approaches the speed of light, it requires infinite energy and therefore infinite mass to maintain that speed. This is precisely why exceeding the speed of light is impossible. What challenges us further is this. According to the physics we perceive, speed multiplied by time equals distance. But when you plug the speed of light into that equation, the laws of physics as we know them break down. Because the speed of light is constant. Therefore, something between distance and time has to give. This theory about the speed of light was confirmed in real life in 1971. In an experiment known as the Hayfel-Keating experiment, 3 atomic clocks were synchronized with one another, and 2 of them were placed on aircraft flying in opposite directions. The third remained at the airport. When the aircraft landed, the clocks were no longer in sync. The atomic clock on the eastbound aircraft was 59 nanoseconds, billionths of a second, behind the one that had stayed at the airport. The westbound clock was 273 nanoseconds ahead. Hard to grasp, isn't it? People generally struggle to accept this. But even a single example from everyday life is enough to appreciate the importance of this theory. GPS systems, for instance, because satellites in orbit are moving at very high speeds, a small time difference accumulates, and this difference must be continuously corrected and synchronized. Without this correction, the location shown by apps like Google Maps could be off by kilometers, and we would be unable to pinpoint anything with accuracy. That is it. Today we attempted a brief analysis of the general theory of relativity, which Albert Einstein committed to paper in 1905. Even when these concepts seem difficult to grasp, they are all subjects that directly affect our lives. People sometimes say, this doesn't concern me, but there are always points where these ideas touch every one of us. I believe that thinking about yourself and the universe is life's way of asking you, understand why you are here. It is truly remarkable to appreciate how much people like Albert Einstein and the other figures in this video have helped us perceive life and the cosmos. We are just getting started on this channel. We'll be exploring many different topics and scientists along the way. In our next video, let's see where we find ourselves, who we'll be with, and what we'll be uncovering.